All right, so I took most of these notes from Andy Field's Discovering Statistics Using R, but it's the same lecture notes as the Discovering Statistics in SPSS, just a different program. So, big goal, what are multi-level models, and then how do I analyze them? And these are the PowerPoints that I handed you guys, so you don't have to try to do 8 things at once. So the big problem, these slides are fancy, there we go. The big problem with data is that it can be hierarchical. So it can have a set of structures to it. And we run into this problem a lot in our lab because we use items, lots of items for participants. And so the data is structured in that each participant gets the same set of items. So not only do we have the participant issue, we have they all see the same items. And so I know the body lab deals a lot with this because they test people over time. So any repeated measures data is also hierarchical. So you have participants tested over time. So more traditional examples are kids tested in classrooms. And so they can only be in one classroom. So if we wanted to test the differences in our class, they would only be in with one instructor. So we don't switch you guys up. And then any type of repeated data point. So the beauty of MLM to me is that I don't have to reduce every participant down to one score to analyze them. I can analyze every single item they ever looked at. And so we go from having maybe there's 4 different types of questions we ask them, but they do that question type like 25 times. So we go from having 4 points to 100. So power on these is a lot better. So for me, it's really great because I can analyze by item or by time point, and I don't have to create an average score somehow. That doesn't necessarily work on scale data, because if you have a scale, generally there is a total score that's been psychometrically analyzed, but this works really great if you have experimental repeated data. So when we get to repeated measures in grad stats, we're actually going to do this exact thing, so you're kind of getting a head start, I think, on next week's lecture. Yay! So kind of give you an example of hierarchical data. And then I'll talk about specifically an example from my lab and from their lab. Is that I have kids here. These never copy very well, but level 1, so there's this sort of leveling to them. So level 1 is the lowest set of nesting, and that's generally where the participants are. So that's the participant level is usually almost always level 1. And then how are those grouped into clumps? Okay. And so this is by class. So I have all these kids in whatever class they're in. If I then add instructor or school, that would be a level 3. So each of these classes is nested within a specific school. So we've got a structure of the data. So you do have to think about this ordering when you're working on analyzing the data, because that depends on what order you're going to list the levels in. I'm going to try to do a pretty simple example, but I also have examples of if you have multiple levels, this is the code you would use. So an example from my lab, so we have each person judging 120 items. This is the thing that Katie's working on. And these items have certain characteristics, and generally we have to sort of average and create a high judgment type and a low judgment type. And so I go from 120 items to 4. So that loses a lot of power for me. So instead of creating these averages, I can use all of them for each participant. And so that's why we like it. It's a power issue. And the reason I got into MLM actually was because SPSS just won't run 66,000 lines. It's just not a thing. R will do it in 2 seconds. So it's kind of an accident. And then I got coerced into several theses now on doing these structures. So I actually really like MLM now, once I got the hang of it. Yeah, it's fine. It's cool. It's actually, I feel the wave of the future. But, okay, so I think we got everybody now. Yay! I'm actually about to talk about your data. So the other type of design that you might have is where participant data is collected on the same DV multiple times. So in my example, it's different versions of the DV. It's all still judgments, but it's different items. And in their lab example, it's the same DV over multiple times. And that's traditionally repeated measures. But if you're going to have 25 time points, most repeated measures designs are not down. So how can I analyze that in a better way? And so I thought this was really funny, especially after this week's cheese adventure. This is actually from the book, and it was late, so I thought I just kind of copied it. But ordinary regression. So regression is ANOVA, right? All the different types of ANOVAs and T of regression, they're all least squares analysis. So they turn themselves into cheese and hide in the fridge. Multi-level models eat regression-flavored cheese for breakfast. Just thought it was funny. And so essentially, what is that talking about? The big assumption that we don't really test, right, is independence. So you want each participant to be independent from each other. Well, if you have participants tested over multiple time periods, they're no longer independent. And if you're going to use all 120 items, they're not independent anymore. And multi-level models are like, independence, we'll deal with it. It's cool. So it will deal with the independence error and give you more power. So what are the benefits? Homoscedasticity, whatever. Because you can actually tell it to give you random slopes. So if the slopes are different for each group, when you look at the data overall, it'll look like heteroscedasticity, because you'll have a bunch of people who have different structures, so it tends to make these kind of triangle shapes. Which generally you go, oh crap, I don't remember what she said to fix that, and then mostly my answer is like, I don't remember either. You go, oh, I hope this isn't a problem. And so you can actually model that variability in the regression slopes. So I actually have a picture at the very end. Finally, this was the last thing I did, so I was a little tired at this point, but I graphed 4 of the participants' data, so that would be a really big problem with variability in the slopes. Some of them are positive, some of them are negative. So that would look like heteroscedasticity, because some of them are going up, some of them are going down, but I can add a random slopes factor and account for that. So that may not be readable on your printed version. So I can deal with the assumption of independence. So I don't have to have independence. Actually, that's the whole point of a multi-level model. So if you don't have a nested structure, it just kind of goes, why aren't you running regression? So I can control for the fact that this is participant 1 10 times. So it's basically repeated measures. And then missing data, and that is probably the best thing about MLM, other than power, is that if you are testing people over time, they're going to drop out, or they're going to skip time point 2, or you're just not going to have data. And so you can cope with the missing data. So the data set I have for you guys to look at, that I downloaded somewhere, where'd it go? Is not quite Jamie's data, but it's close. I tried to force it to do things last night it didn't want to do, but I have a good example of what her data set would look like. So, well, I was trying to make them more mnemonic names so it would be easy to remember what they were. So she's testing people 5 days, 5 times each day, so I have day and time. You have to have a participant number, because that's usually one of the variables you want to nest for. So it's the level 1 hierarchy. So you need a participant number for this type of design to work. An intervention type, and then this is actually the DV across several different types of ways to measure body checking. So stop me if I say something wrong. Okay. I kind of I don't know if this is the way you actually want to analyze it, but I made something up for that. Okay. So this data is actually in both wide and long format at the same time, so we'll talk about how do I solve that problem in a little bit. But I have to have a participant number, but if you look at, there should be 5 time points within each day for each participant, and clearly that is not true. So if I were to sort by participant number and time, okay, so, well, participant 1, who's probably Jamie, has all 5 time points. But participant 2 on day 1 just did 2, 3, and 5. So it's actually missing data. We're not going to code an extra line and make it missing, but it is missing. And so it will interpolate between those other time points. Because
you don't have to have a line that's
no. So that's good, because you don't have to enter it. But then if you do have missing data, wherever it went, yeah.
And Erin, what will it interpolate on the last point and the next point?
Yeah, well, it kind of depends on, if you're going to use time as a variable, yes. If you're going to control for time as a nested structure, somewhat. If that makes sense. So if on your analysis, if you're wanting to use time in that way, I would actually make day and time one column that's got 25 time points. But you could also do time is nested in day, right? So the structure of their data marker is actually like this. So I got participants who take things 5 times a day. And then depending on how you want to use the items, you could also consider the items a nested factor. But 4 levels gets to be like, make it stop. So you could nest it this way, or you could collapse day and time into 1, depending on how you want to use it. But mainly the answer to your question is yes. I'm only using time in this analysis to kind of make it easier, so it's actually just, it's going to ignore time 1 for them just in general. Like there's nothing to interpolate on. So like person 2 here would only get a slope from 2 to 5. Yeah. But if I had the previous day, it would do the previous day to that point. Yeah. All right. So the missing data is also a really huge deal. Okay. All right. Now, one of the big problems you can have is if it's missing on a variable that you're most interested in, because then it will ignore the whole time point. So in our data set, we have some people who didn't take one of the IVs. And so they have just a blank column for all of the items because the IV is trying to be correlated with the items. And so we lose all that data because we just don't have one of the IVs. It's not perfect, but it does help with missing data. And I said this a couple of times, power. Okay, so it's much easier to estimate small effects. So if you're looking for small changes over time that are still important, this will work better for you. All right. So we've talked a little bit about their data. So the level 1 part is participant. So that's mostly what I'm going to model. So almost always participant is level 1, which means they're like what most of the data is nested by. So control for the fact that these are all correlated because they're the same person. But we also could nest in other levels. So they have that type of question we're using for the DV, and for the time point during the day and the day itself. But since I think time is a variable this time, yeah, I can never remember. I don't know, maybe? You're wanting to decrease after the interventions, so maybe time is a variable. I threw it in because it made it work better. That might be better to collapse day and time into one variable, make it 25 time points. So
if there was no like intervention or everything, if all the time points were equivalent, then you would.
I could, but
time together.
I would still probably do that because you could also. I have an IV that's intervention, so you can have it as no, 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 type 1, type 2.
That's the way Emily set hers up, was like 25.
Right. Yeah, it's a little easier because then you're not having to nest twice, or at this point maybe 4 times. But you could do it either way. So you have to. This is the important part you have to think about. Like, how do I want to try the nesting? Okay, so it's called nesting because you're like structuring the data. Okay. So the DB is body checking. In reality, what we'd probably have to do is do this as a slightly different type of regression using a Poisson distribution because there are a lot of zeros. So remind me afterwards, I'll tell you about that. But just pretend this is continuous and beautiful data and it's normal. Okay. So fixed versus random coefficients. So basic regression and ANOVA is all fixed coefficients. So you're estimating one score for the entire group or one score for the entire range of data. So you're getting a mean or A, R, or B, or whatever. Okay. So the intercepts and slopes are the same across everybody. So you're estimating one slope, one intercept. Okay. And that's the way all of regression and ANOVA work, okay, for these squares. Random coefficients are so much better. I'm partial here, clearly, because it allows you to let them differ. And so this is really true of participants. So this is kind of like a latent growth model. So we did this summer, yeah, where you have participants, like here's the average score for participants, but some people are going to start higher, some people are going to start lower, and that right now is just error. So you don't know why some people are higher and lower. A random intercept will let that start at different places and will no longer be error. So it controls for the fact that people start at different locations. So you think about a smoking cessation, I can't say that word, quitting study. Right? People start all over the map. You got some people who smoke a whole lot, some people who only smoke a little bit, and so they start in very different places, but you're trying to get the end goal be the same. but your regression will actually be very bad at the beginning. So I can kind of draw that. So I talk about this a lot with sporicity, problem with sporicity. So if I start, here's my range of smoking at the beginning. Some people might smoke a little, some people smoke a lot, and then overall they all end up down here at the bottom. But that's actually a sporicity issue. So it's too much variance at the beginning, not enough at the end. Right? And so a basic regression would estimate one intercept and one slope. Right? MLM would allow you to have slightly different intercepts for different people, and you could actually have slightly different slopes. So those would be random. They're not random in the sense of like you just pull a number out of the air, as in they're different for different people. So that also will often let you find interactions you didn't know were there. Because random slopes is not necessarily a good thing. Like you don't want some people to go up and some people to go down. But if your random slopes are significant, maybe you can figure out why some people are going up, some people are going down. So what variable might be interacting with the slope variable? All right, and anytime, just stop me if you're not getting something. So I have some pictures from the field book. And this is actually the Viagra example that we just did in class randomly. So I thought that was kind of like a sign that was a good time to do this. So we just did this example as a NOVA in class. The dotted line would be estimating a fixed. Okay, so that would be a NOVA or regression. But a fixed slope, so everybody has the same slope, but a random intercept would fit the data a little better because they're starting at different levels of libido in this example, and the slopes are all the same. But we're allowing them to have different intercepts. A random slope but fixed intercept, this isn't perfect because they don't look like they cross the y-axis in the same place, but so this is the intercept, but now the slopes are all different. I don't know how often that kind of thing is going to make sense, but you could try it, or you could do both. And both might be the best interpretation for your data. Because not only are they starting at different places, they're getting different slopes, and this is when moderation, so an interaction analysis, is really useful. Because why are they having different slopes? Okay. So which one do I do? Do I do fixed? Do I do random? How do I do this? Oh, you can test them against each other, and it's actually like stupidly easy. I thought I was doing something wrong last night, so hopefully I will make it seem stupidly easy to you guys too. Okay. So most likely, at least random intercepts and maybe random slopes are going to fit the best. In the data that we have, random intercepts fits really well, but slopes does not, which would be kind of a good thing because you want everybody to go down. You were hoping your intervention, God, I can't talk, is successful. So everybody's body checking is going down because body checking isn't good for you. Okay. Which is like a gross oversimplification of everything you guys do, but I'm the stats person, so. Okay. So just like you were going to do a structural equation model, these have to be built up gradually. So you're going to start with like the simplest model possible and then slowly change one piece at a time. So when it blows up or hopefully runs smoothly, you'll know what it was you did that caused that effect. Okay. So we can start by doing only intercepts, add in the fixed effects, and then add in the random effects to see, okay, what is working, what isn't working. Okay. And then when they don't work, you have a place to start looking on why it's not working. One of the frustrating things about this is when it doesn't work, it just says failed to reach convergence. And that's almost all you get. So that's the big problem, is the error messages are not always the most helpful things. Okay. So we're going to compare the change in log likelihoods. So I'm going to get to that, what that is right here. Okay. So there's two ways to assess fit. And the first one is, I think it's Akaki. Not sure how to say his name. The AIC. And then the BIC. So they're both information criterions, which means they don't really have scale. They can be through 1,000 and be good. So there's no cutoff criteria for them. So it's not like P less than 0.05, which is kind of frustrating. Okay? But both of them are set up where lower values are better. Now, the other problem with them is that there's no criteria of how much lower it has to be for it to be significant, which is why they haven't really caught on in structural equation modeling. People use these, but like if they're 1 point different, is that significant? Like, I don't know. But lower values do mean less error. So you'll see these when we run the output, but they're not always the most interpretable things. Okay. They do have penalties for more complex models, but they both do. So as you add more to the model, the scores are going to go up because it's going to penalize you for making a more complex model. But that does not necessarily mean that the last model was bad. It just means that this model is more complex. So they don't totally get used a whole bunch, but people report them. So it's kind of like, I'm reporting this, but it doesn't mean anything. So it means things, but let's do the other way instead, which is log likelihood. So log likelihood is a ratio, essentially, of good variance to bad variance. And it's chi-square distributed. And so I actually explained it all out, and then I realized that R would do it for us, but let me tell you how it works. So what it does is it takes the log likelihood from one model, it subtracts the second model, and creates a different score. So this is how different these two models are. And then you look up whether or not it's significant by using a chi-square critical value. So to do that, you subtract the degrees of freedom. Often they're just 1 degree of freedom different from each other because you're adding one little piece at a time. But if you add a variable that's got 3 levels, that'll be more degrees of freedom, but 1 to a couple degrees of freedom difference. And then you would look up a chi-square value for 0.05 or 0.01, whatever one you want to use. And so you have a chi-square difference score, degrees of freedom difference. Is that significant? The ANOVA function in R will let us it will just do the magic for us. But that is what it's doing in the background. So that's how it's calculating if they're statistically different or not. So I must have this slide like in 100 different sets of notes on what you're supposed to check for assumptions. But I thought it would be fun to like mark them out this time. So, like I said, it was late. So you still have to check for accuracy in your data, like that's always true. Don't have to worry about missing data, right? Or you do have to check for outliers. I am not 100% if you're supposed to do that in wide or long format. Nobody's really like figured that one out. So we're going to kind of test that idea in the lab. By we, I mean poor Katie over there is going to get to do it. You do have multi-collinearity issues, and so if you get a singular matrix error, because your variables might not be correlated, but once you control for participant residuals, like their correlations between participants, sometimes it will make a singular matrix. Because let's say you're controlling for just one of the nesting levels, and the other one, once you add it in, is like, wait, this is too perfectly correlated, and it'll freak out. You can center them. I always say try running it first and see what happens, because then at least the coefficients are in the raw scale. They're in the scale of the data. And then if you have to center them, do mean centering. So you just subtract the mean from everything. Okay. That's very similar to what you do in like interaction moderation analysis, because when you add interactions, it tends to cause multicollinearity and you have to center them. And that is the scale function in R. Linearity, because this is still linear, multi-level models are still linear. Normal and homogeneity, but not so much homoscedasticity, because you can test random slopes. So it's kind of cool, we get to mark them out. Yay! Okay, so especially for non-R peoples, I was hoping we could kind of do a little bit of getting it imported before I talked about like how does all this code work. So when you have a struggle, I don't want to look at you, but they're taking my class right now, so please say something. Okay, so the reason I love RStudio, there are lots of reasons now, but one of the main reasons I love RStudio is that you can import the data sets very easily if they're in CSV format. If you're going to use another format, there's some functions. So if you're interested in like how do I import from SPSS, I can tell you, or like anyone over here, hopefully can tell you how to do that. But I kind of did it two ways. So file.choose is a function that will like pop up a window when you run the line sometimes. It hides in the background, and it'll let you just pick the file you're interested in. But the basics of RStudio, since a couple of you haven't seen it, is, okay, so this window here, what I did was I opened that syntax. So this is that syntax that's on the website. Did everybody get it downloaded? No, okay. We'll pause. We'll download the syntax. Also in an F. All right, so back to opening files. So probably the easiest way is the import dataset option. So you click on import dataset. It's over here in the environment window, and allows you to pick from text file. What they really mean is from CSV. Okay. And then I have to find where I hit it on my computer. So you click on it, and then it shows me what it's going to look like. So I can call it something else. So I don't want to call it that. I called it data file so that the rest of this code will run appropriately. So data file. And you want to make sure that the heading here is yes. If you have your variable names in the first row, can you see? Everybody, you're like, yeah, so you want the heading to be yes. If you do no, it's going to import everything as text because the first row of data is text. Okay. So be sure you click yes. Okay. And then import. It will automatically show you what the data looks like. So the other way you can do it is use the file.choose option. And so I had just an example of what that looks like in the code. So if you already got the data file imported, don't run line 5. But what it does is it allows you to pick the file on your computer. So once you get the hang of opening these files, that code can just go in any file. So it's a little faster because then you're not importing, like cooking 8 more steps, but whatever you're comfortable with. CSVs are definitely the easiest thing to import. And the cool thing about Qualtrics is it'll let you download in CSV format. The problem with the Qualtrics data is it has 2 header lines, so you have to kind of edit it. But your data I had to edit anyway. So we did figure out how to import it where you can ignore the second line, but this data set was like a merge of a bunch of different ones. Yeah, a couple of them. And then I got tired. You had so many different ones. Yeah. So, all right, so if you don't have the packages you need today, so packages are add-ons. They'll allow you to do different analyses. So R comes with base R, which is just like your normal regression ANOVA. And if you want to do anything extra, you have to install it. So there's 2 ways to install it, because there are multiple ways to do everything. So you can click on packages. So all of you guys will need to install nlme. Right. I click install. You do have to be on the internet for this to work. And then you would type the name of one of the packages. So reshape is one of them. And it'll start to pop up as long as you're on the internet. And you just click install. Or what I did was I included the 3 lines of code. Okay. So 10, 11, and 12 are also the packages to install. So anything, I realized I hadn't said this yet, sorry. Anything you have up here that you want to run down here, so nothing is being run up here, it's just the code. Down here, if you want it to run, what you can do is when your cursor is on that line, are you on a Windows machine?
Yes.
Yes, so Control Enter or Control R at the same time. And it will copy the line that you're on down to the bottom.
It will automatically run it?
Yeah, that's what it's doing. Or you can click Run. But if you're typing, Control Enter is just much faster. If you're on a Mac, what did we decide was? Command Enter? Mm-hmm. Yeah. Not Command R though, that's lame. So Control R for run if you want to remember it that way, or Control Enter, let's go. So you will want to run 10, 11, and 12, and that will install all 3 packages that you need. Okay, so you guys make sure you get nlme in there. Yeah, so reshape, nlme, and ggplot2. And I wrote them all down. No, I didn't write ggplot in here.
nlme take an excessive amount of time?
Do you have the little stop icon?
Yeah.
It shouldn't. It's not SimPaths.
Oh my gosh. Get it? No. Stop it.
I'm not sure what's going on, but
There's an
oh. Did you get it, Jamie? Or is it still frozen?
It finally went.
Okay, good.
It's just,
It might be slow because your internet's slow.
yes.
It could be what everybody's trying to do.
Oh yes, give me all the crayon. Okay, let me back up a couple slides. So after you get them installed, that's awesome. And this is the thing that I think I forget the most, is it doesn't mean that it's actually on. So anytime you install a package, it stays on your computer unless you reinstall R. So if you update your R, it will wipe all your packages. And so this is essentially like SPSS if it had a function to do regression, but it didn't ever load. So you have to remember to load it every time. What that does is it saves you computing power because it's not loading things unless you need it. So it will save your computer from running a whole bunch of packages because at some point you end up with a bunch installed, but you will forget to turn it on. And I jokingly say all the cool kids do it because I have plenty of videos of me recording being like, why didn't this work? Oh, I didn't turn the library on. So when they're installed, they're called packages. When they're running, they're called libraries, which makes no sense to me, but anyway. So there's two ways to start up a library. And I thought I fixed this, but you can click on them over here. So when you click on packages, now those should show up. So you can just kind of click on the checkbox, and it will open it up. So what do we got? ggplot, nlme, which is hard to say, and then reshape. Or I got lines 16 through now 18. That's the code for it.
Once you click on it, do you have to do anything after that? Or?
No, it's loaded. So you should see that it came up down here, a little code that says library. So I just recommend putting them in once you are, not so afraid of the syntax. Putting them at the top of every code so that that's the first thing you run when you reload it, so that later you're like, wait, why isn't this working? What it will tell you error-wise is cannot find function, whatever function you're trying to use. And so that's a good clue, like, oh, I didn't turn this on. So I do it all the time. So the other two concerns are factoring variables and reshaping the data. So that's what the reshape function does. Not reshape 2, just reshape. So if I have a categorical variable, it has to be dummy coded for regression to work. So I coded Jamie's as like no intervention, type 1, type 2, because they've got a couple of types. And so I want to set that up as a factored variable. And this is different from setting up a variable as nominal in SPSS, because that does not dummy code it. It just gives you the category so you can run it ANOVA. But a factor variable in R will dummy code it. So I don't have to explain all the joys of dummy coding. The factor function also allows you to add labels and reorder the labels. So if your data set has text, when you're pulling it in, when you're importing it, it will automatically try to make it a factor. So it does a smart import, like, oh, this is text, and the text reoccurs like 25 times. This must be a factor. Figures it out. However, it imports them in alphabetical order. So if you want them to be time 1, time 2, time 3, and it imports them in alphabetical order in a different way, I know that's alphabetical, but go with me here, you can reorder them with the factor function. So we had an example from the homework where it's like novices, intermediate, advanced. So it imported as advanced, yeah, so we had to reorder it. And then this week I was like, by the way, I never told you how to do this. So the first thing I'm going to do is just show you how do I set it up if it's already coming in as numbers. So that's the factor function. And so without getting too crazy into like what all the rules are, but the factor function has to have a column name, so you can't factor a whole bunch of columns at once. You have to do them one at a time, as far as I'm aware. The levels equals, the C function just says, here's a list of things that I want to do. And those have to be whatever the numbers are in the data set. So if you have 0, 1, 2, it has to be 0, 1, 2, or it will wipe them out. Ask these people. I'm fixed. The other way that's just to reorder, ours are in the right order because that is alphabetical, none, type 1, type 2, is the same code. So factor, so the column name, and then just levels. So there's no labels. Labels you're only going to use if you want to rename something. So if you realize, oh, I called that the wrong name, you can fix it. Levels is just like reorder the levels this way. But they have to be typed exactly the same as they are in the data set. So that's why I always run the table function first, so I know how they're spelled. And that will let you reorder them into a different order. So if I wanted to do type 2 first, I could. Okay. If you have trouble with that, I mean, just send me an email. It's pretty easy. Okay, so now we have our intervention variable factored out. So if I run that table again, now it has nice pretty labels. So I know how many people are in each intervention, how many points there are in each intervention. Not necessarily people. The other issue is wide and long format. So the data set has to be in long format, okay, which this data set's a little weird because it's actually half and half. So wide format is traditional, where each participant gets their own row and the columns are all the variables. So you'd have like 25 different columns for all of your different time points, times the number of questions that you'd have. So you would have 25 different time points times, I don't even know how many body checking things were, 8? Yeah. So that's how many columns you'd have. And once you do the hang along format, you'll be like, why do we ever do anything in wide format? The long format is where each measurement gets its own row. And that is the only way this will run. And so, like I said, Jamie's is half and half because each participant's time point has a different row, but right now all of the items are still in wide format. So we're going to melt those. So melt is a really cool function. Its partner in crime, cast, is not a cool function because it does not have easy code, but melt is fairly easy code. So the code is melt. So you type in the data frame name. So what do I mean by that? I mean the name of the entire data set, so data file, and not any particular column. So we want to change the entire data set. ID variables, so these are a list of variables that you don't want to change. Okay. So remember, C just says, give me all of these things. This mouse is possessed. All right. These stay as their own column, but they get repeated. So it will be like participant 1 will get repeated 8 more times for each time point. Okay. Or each time point. Measured variables are the ones you want to collapse all into one column. So I'm going to take all of 8 of her columns and collapse them into one. Okay. Yes?
I'm moving them like this, just moving them like this.
Yeah, exactly. Okay. And Melt will do that for you. And that's why you need the reshape library, because Melt is in reshape. Okay. So I have that here around 28-ish. So I have the data file name, and I've separated the lines out just so I can see what's going on. You can make it all one line. So data file is the name of my data set. I'm saving it as long data, so I have to save it as something else, or it will just print out the data set. So in general, if something prints out, you haven't saved it. Okay. But print out, I mean it comes up down here. So data file name, ID, these are the variables I want to stay the same. So day, time, participant number, intervention, like I don't want to change those. The measured variables, wow. It's, yes, measured variables. Did I leave weight out? Almost certainly did. So I left one of your variables out by accident. Cool. All right, well, I could add weight in here because that's actually another one that's in that column. No. The names of the columns have to match that code, or it'll tell you can't find the column. And it is wildly inconsistent when you use quotes and when you don't use quotes. And it is also wildly inconsistent on when you use the dollar signs and don't use the dollar signs. So that's something you learn through trial and error. And so this would be all of the names of the columns that you're interested in melting into one. And remember the little C function just binds them all together. C stands for combine or concatenate.
And then do we run that?
Yeah, so all 3 lines. And you'll get a new data set. Hopefully, without any trouble. So now I have the long data set. And if I collapse so I can see them next to each other, you'll see that I got way more lines. So the first thing where it says obs is the number of lines, and then variables is the number of columns. Did it work? Everybody's running okay? Okay, cool. And then I left you a note about the only bad thing about Melt is what it actually does to the column names. But I don't want to get too crazy today. And so it automatically labels them variable and value, which is quite possibly the silliest thing. So variable is the literal like column name that it came from. So my variable column is now all of those column names. So it creates a factored variable. So it'll have like weight, jiggle, thighs, all those.
And why is that bad?
Because it's not descriptive. The name of the column is variable. I don't know.
Well, wait.
Like,
Where's the weight and thighs?
no, it's not bad. The squishing part isn't bad. So it kept them, it created a categorical variable so you know which column it came from, but it called that variable column name variable.
Oh,
If you
instead
do
of
the
like,
view function, you can kind of see, like,
Yeah, or if you click on this little icon over here, the little Excel looking icon. Yeah, you get it? Yeah, I was like, wait, the view is capital V.
yeah.
So it's called this column name variable. I just think that's dumb. And then value is the DB one. So you can change the names of the columns, but I don't want to get into that. So I left a note here, like, this code assumes that you did not change the column names. Now, if you had multiple DVs and you wanted to melt them individually, so let's say you had, these 4 are one type and these 4 are another type, you would run melt twice and then stick those 2 data sets together. We kind of talked about this one day. I can show you how later. But you would have to run melt 2 different times because it will stick everything in the measure column into one column. So like Emily's study where she had the panis and something else, so it was 2 different DBs, I would melt once for the panis and once for the other one.
oh, and then you combine
Bind them together. Yeah, because otherwise it will create you one column with all of those. Yeah.
And when you're doing this melting, it's actually creating 2 columns because you have one column that's called variable, but it has the different labels,
Right.
and then the number associated with that.
So when we talk about repeated measures in SPSS, people have a hard time with which one's the IV, which one's the DV, because the IV is the labels of the columns and the DV is the number in the column. This solves that problem actually, because the IV is literally this column with all these labels, and the DV is this body checking, and then I have the type of body checking that I'm measuring. That's why I like long format, because it's much more like, oh, this is the IV with all of its labels, and this is the DV of body checking. But then you have to remember it's repeated on your own. Okay, so we actually want to run an MLM now. Yay! So now we've set everything up to be ready. So it does need to be in long format, and you will want to factor your variables. So otherwise it will not assume that they're continuous, and that wouldn't be true in this case. So we're going to start with a baseline intercept only model, and then we're going to do a random intercept model. And then after those 2, we'll take a quick brain break, and we'll compare those models. Okay, so baseline intercept only is essentially saying, I want to know y equals only the intercept, so the mean. So we have no x variables out here, so only the intercept, which is the mean of the y. And then we're going to allow people to do different things. So participant 1 can have a different mean than participant 2. And I'm just calling these model 1 and model 2. That's not a normal thing to call them. People call them the baseline intercept model and the random intercept model. That was too much to type. If not, so if model 2 is better than model 1, you need to do the MLM, because that implies that there is something with the nesting that's important. If not, in theory, you can do a happy ANOVA dance and just run it as ANOVA. The problem with that idea is that most reviewers with this type of data setup want you to do the MLM no matter what. So, especially with very hierarchical data like y'all's data is. Okay, so how do I do that? So the basic setup for any type of regression function, ANOVA, whatever, is that y, and that's a tilde. Ask Inga how much she likes tildes, because she doesn't have one on her keyboard. X. So y is approximated by x. So this goes back to like writing it in regression math. Data equals the name of the data set, and then depending on what you're doing, other important stuff. I know that's very descriptive, but it depends. So, and I tried to write just a whole bunch of notes in here, so later you could be like, what was she saying again? Plus, you can listen to this again, complete with all my quirky moments. So So the intercept-only model is actually generalized least squares. So, everybody get it? Yes. So generalized least squares is basically normal math. Right? We almost always do just least squares regression. Generalized least squares is just a slightly different type. And then we're going to make it run with maximum likelihood estimation. So we're kind of moving away from traditional regression because that is all least squares. It's a closed form solution, meaning it's like mathematically solvable. But doing it with maximum likelihood, that's just a way to iterate through a bunch of different options. Okay? I can explain that more if you're interested, but mostly just trust me, max likelihood is just a different type of math. Okay. So I'm going to set model 1. I'm going to save the output so I can look at the summary of it here in a second. So it's GLS. That's in base R. So you can run this type of math anytime. I can actually make this bigger. I'm sorry. It's a limit to how big you can make it, though, before it's just ridiculous. So we're going to do value. So that's my DV. It's in the long data set. It's called value. So DV goes first, tilde, and then a 1.
The value is the number of times they did that?
Yeah, so the number of times body checking happened. And we're ignoring the type of checking right now. So the tilde means approximate this with, so don't use an equal sign or it will freak out. 1 means do intercept. Okay, so don't estimate anything but the intercept. That's almost the same thing as saying give me the mean. Data equals the long data set, because otherwise why'd you make it? And then these two just need to stay no matter what. So method equals ML for maximum likelihood. NA action equals NA omit, and there are several different forms of this, but this works so that if you have missing data points, it will ignore them. Okay. Otherwise, it'll give you an error. So I'll run all those lines at once. It didn't give me any output, so I got to ask for the output. The summary function gives you the ANOVA tables. Well, it gives you a bunch of random stuff, but here's the ANOVA table. And I tried to copy it so I can blow it up a little bigger. So generalized least squares fit my maximum likelihood, so it tells me my model again. And then it gives you AIC, BIC, and the log likelihood, which, like I said, are numbers that don't necessarily mean anything. Neat. The next thing is it means my coefficients. So that gives me the intercepts. So that is your average body checking right now, 0.4. Okay. Standard error, my p-value, so that is significantly different from 0. This is an intercept-only model. Shows you the residuals, and then the degrees of freedom. So if you were trying to write this up, you could use that degree of freedom for your t-value, and here's p. So an intercept-only model is significant, which isn't too surprising, so that means that the body checking is more than 0 at the moment. Okay. But what I really want to do is compare this model to a random intercept. So we've got an average intercept versus a random one. So do I have to nest this data? And then I did that.
So this is like your 0.4 is, there are some people who aren't checking at all, there are some people who are checking a lot, and now doing the random, you're taking account for their baseline.
Right. Yep, exactly. A+, gold star. All right, so it's Friday morning. I've barely had any coffee. So the random intercept-only model, now we're going to use nlme. There is another package called LME4. I didn't recheck this morning, but I think LME4 does not give you p-values for some weird reason, so that's annoying. The old version didn't, the new version might. nlme will. So the function is LME, the package is nlme for nonlinear mixed models, but it also will do linear mixed models. So it's a package that'll do both. But the function for it is just LME. So we've switched essentially from GLS, so generalized least squares, to LME, so different estimation. And then
LME stand for?
linear mixed effects, I think. I don't remember. Why are you going to ask me hard questions? Mixed effects, yeah. So people call these multi-level models hierarchical level modeling, mixed model repeated measures, and also linear mixed effects. They are all the same thing. That took me a long time to figure out. Like, what do you mean HLM? Don't you mean MLM? Wait, are you talking about MRMM? Whatever. They're all the same thing. By the way. I think the hip thing now is to call them MLM. So value equals 1, data equals data, method, blah. So all of that is the same. It's the exact same code. Says I want to do the same model, but here's the part where the random stuff comes in. And the coding for this is a bit odd. It took me a minute to get. But essentially what happens is it has to have a tilde. So estimate with. So anytime you see tilde, they mean approximate something. The 1 means intercept. So everything on the left side of the straight up and down bar is what happens on Y. Everything on the right side is what happens on X. So intercept, and then estimate a random intercept for participants. So part no is what I name the participant column. Yes. If you want to do multiple ones, there's a couple lines down that gives you an example. So I'm going to run all of that. Like I said, stop me if something isn't making sense. So that gives me this output. Now that I have 2 AICs and 2 BICs and 2 log likelihoods, I can compare. By themselves, they don't necessarily mean a whole bunch. But it will show me my random effect. So it gives me the intercept, the standard deviation of the intercept, rather. So the average score is this 41, 42. But if I make it random, here's how much they're varying around that. So considering the scale is like 0 to 10 at the moment, it's kind of considerable. The next thing it gives me is my fixed effect. So actually, when you include the random effect, here's the average. So the average went up because it allowed them to vary a little bit. And that's still significant. So random effects are especially on participants and the intercept side are usually probably going to be significant. Not always. Sometimes they're not. How do I compare those? Well, I could just look at AIC and BIC. It's clearly lower in the second model. But if you want a real hard line in the sand and a number, you can use the ANOVA function. And so that's why in class we weren't using ANOVA, because it does not actually run ANOVA. It compares 2 different models. So the ANOVA function does not do ANOVA, by the way. It compares 2 different models. It does not run a basic ANOVA. And so you just do model 1, comma model 2. Run that. And then it will show you the comparison between the 2. So it just kind of lines it up nice and pretty for you. And you can look at it yourself, but this is much easier. Look, it's significant. So it's comparing the difference between these 2 models, so 1 versus 2, and then that tells you what the difference is and if that's significant.
Is this something you report in the results section, or would you just say we chose to do this model?
I've seen it both ways. I generally just go with, let's just run it with the random intercepts because they're going to want us to do that anyway. And then if they ask me to prove that that's better, this is how you'd say, yes, random intercepts are better. We have tried it where we said random intercepts aren't better, so we're just going to do a regular old ANOVA. And they're like, no, you can't do that. I'm like, fine. So, and it actually worked out better to nest. So,
Okay, clarification
Yeah.
on what we're getting from this. Are we looking at the p-value for telling whether it's
models,
better or-
the models are significantly different.
Okay.
And the model 2 has the lower AIC and BIC values and log likelihood, so it is better.
So we are looking for the one with the
Lower values, yes.
Okay.
And since model 2 is better, that means that we should continue to use random intercepts as we go. Yeah. All right. So there we go. So we showed that, oops, wrong button. Nesting by participants is important. And then if you had, let me go back to the code here. If you had multiple things to nest by, I kind of showed you what that looks like. I'm not going to run them that way because this data doesn't totally want to do it because I don't have quite enough data points at the moment. But basically what I've changed from having 1 nesting variable participant number to 2 is I just changed the way the random looks. So it's a list instead of C, super annoying, because you can never predict what it's supposed to be, list or C. So list creates a list, like a grocery list. And you want to do them in order of the nest. So level 1 is the last one, and then level 2, and then level 3, because otherwise it'll try and nest them backwards. So the highest order of the hierarchy needs to go first, and then the lower orders. So each person is nested within the time variable, which is during the day. And then I could also add during the day as one. And it will give you, if I run that, this one ran, yeah. Something a little different on the bottom when you have multiple nested variables. So it shows you participant number in time. So it's saying each person based on during the time of the day. And then it shows you how many people or how many points there are in those pieces. Okay? But it still treats it as one intercept because we're not adding an extra intercept, we're just adding how much it's stacked. Okay, so this is controlling for multiple levels of error. So they're nested because they're all the same people, but it's also all the same day, and then it might be across different days. So this allows you to control for error across multiple levels of hierarchy. Okay. And what you would do to test if that's necessary is test model 2.1 here against 2. And then if you add the next piece, is it significantly different than the last one? So you kind of keep going until they're not different anymore. So you may not have to nest for day because it may not be any different than nesting during time. So this allows you to test multiple levels of hierarchical structure.
And you're just comparing those AICs and BICs.
Right. And so I could do a ANOVA, Model 1, Model 2, Model 2.1. Okay. And it will test them in the order, so it only tests them the one previous. So doing them in the order you're interested in with the steps is important. Okay. I didn't continue with that model because it wouldn't run. So I just was now moving on to how do I actually run the regression. Wrong button. I know, right? It's going to freeze my computer because it's the slowest program. There we go. There we go. So how do I add in now what I'm actually interested in? So fixed effects are your actual independent variables. So how do I now I've controlled for random intercepts, how do I test the actual IVs? So I'm going to change out that 1 for intercept only model to the variable names I'm interested in. So I did intervention type on this one. It could be anything. We could test the variables, so are there differences across the different types of body checking? But since there were 8 levels and I only had, I think, 4 people in this data set, I tried not to do anything too complicated. So from here, I changed out this 1 for the intervention.
So the first time you did it, the interventions, that wasn't even taken into account. No intervention, which
Right.
intervention, it was all together.
Right. So now we're doing y plus, equals the mean, so the intercept randomly plus intervention. Whatever. Try again.
Sure.
Yeah. I can't spell. This is not a shock, I hope, to anyone. So I'm saying keep my random intercepts because they were significantly better, but now let's talk about the actual variables I'm interested in. So is the intervention working? Okay. Since I have it coded as categorical, it's going to give it to me in dummy coding. And that's why having them in the right order is important. So it's going to compare everything to the first time point, so none. So if you wanted to compare everything to the last time point, you could reorder them. Right. So dummy coding, remember, it compares everything to the 0 group. And so it automatically codes the first one, the none category, as your comparison group.
None is a no intervention.
Right. So all I've changed is that 1, switch it out for the variable names, and you should probably add each variable one at a time. So if you have multiple variables and it doesn't run, try running just one at a time. Little pieces at a time. This hand motion. Okay. So I'm going to run Model 3 here. So that should give you this picture. Hopefully I have the right one. I tried a couple different things last night to make sure it would work for us. And so it gives me all the random stuff still, but I didn't copy all of that. So it still tells me about my random variable and how much. So the intercept, so the average score is now 0.68, and the standard deviation around that, so the spread around it is 0.4. Is where most people are starting. But it also gives me my intervention. So that's type 1 compared to none and type 2 compared to none. So this is understanding categorical predictors in regression. But if you interpret this, since it's categorical, as the difference between groups. So from none to intervention 1, they're dropping 0.23 body checking behaviors. So the scores are going down. And then from none to intervention 2, the scores are dropping 0.25.
So what does this mean by none? This is like all
No
the
intervention.
nuns,
Yeah, before the interventions start.
but then intervention, and then there's a none. And then
Yeah,
there's
it's not
intervention.
perfectly coded data.
Okay.
Yeah. But that's why I said it might be better for you to separate the two out. Yeah.
So this is saying like none overall compared to intervention.
Right. None.
What is intervention one, Jane?
They get a text message that says like cognitive dissonance or teaching about the effects of body checking or something to make them like a visualization, deep breathing. Something.
Okay, and what's intervention two?
Well, that's all the interventions are different things like that. I think one is research shows that body checking has this effect, and then intervention two.
This is slightly made up data too. So
The what?
slightly made up data. This is most of her data and then a couple of extra time points because otherwise it wouldn't run. Because we didn't have quite enough. There were only 4 people in each intervention.
And there's technically 5 interventions, and this is just 2 of them.
I don't know if you want to code it that way, but this is what we're the
Each
pretend.
person getting all the interventions?
Correct.
I didn't want to do 5. I was like, I'm tired of cutting and pasting data at this point. But the intercept is significant, so we still have a difference in body checking from 0, and then each intervention is different from the none group. If your predictors are continuous, you interpret it just like a regression b-value. So if you instead were using time, which I think I added in here in a second, you could think about it across time. Are they going up or are they going down? And so it gives you the p-values. It gives you t out here. So it's pretty, the reporting style is just a t-test. And you would use, it gives you degrees of freedom somewhere in here. I think it's this one. No, here, DF, right here in front of my face. Sorry. So degrees of freedom, my t-value, and p. So you would report it just like a t-test. So at the moment, in our slightly real, slightly made-up data, they're marginally significant, right? From no interventions, and they're going down, which is good.
Okay, sorry, one more question. So
Yeah.
this isn't like a standard regression where you're looking at like an R change of 1%. Like this is actually independent. So like it's like it goes down by 0.23 with intervention 1, and then it goes down by 0.24 with intervention 2. It's not accounting for that, and intervention 2 is 1% more of variance change.
They do account. They do. It is tested by itself, like against, I guess it'd be PR or SR in the traditional regression. So they are controlling for each other. So controlling for none to intervention 2, here's what intervention 1 is doing. Does that answer your question?
Say that last part again?
Yeah, so controlling for the other comparison, here's what this comparison is. So yes,
Okay.
it is controlling for the other one.
Okay.
Just like if I had 2 continuous variables, the overlapping variance doesn't count.
So this is the effect that intervention 2 has on its own.
When
After controlling for
After-
intervention 1.
Yeah. Okay.
If you want to code it this way. There are other ways you can code this too. Just this worked last night, and it worked in my brain. So there's not really, if you're used to reporting regressions, you get the overall model statistic. That's not a thing. Okay, so instead, I would compare it to a intercept-only model. So you don't get the R squared out of this. And there's a lot of questions on how to do effect sizes for these models. We've been looking at it a little bit in our lab. By we, I mean Kayla, I think, figured it out, and she's still trying to explain it to me. So what I would do if I wanted to know, is this model better than our intercept-only model, is I could run that ANOVA again, and now I've just added model 3 to it. So you can see we're slowly building up the models. Oh, did I? No, I didn't include it. So if I look at model 1, 2, 3, it's actually not significant, but that's because neither of those variables were significant, but it's close. Right? So it's actually the average of those two p-values. But so as I added the intervention, it's not significantly different than an intercept-only model, but I would probably say it's marginally significant because it's 0.08. And so that is where the overall model comparison part comes in.
It's not significantly different than intercept only, or not significantly different than the random one?
The random intercept only.
Random,
Okay, because the random intercept only was better than this. So we said model 2 is a better one. So we're going to keep going with model 2. Now, adding the intervention doesn't add enough variance to make it significantly better. Okay. I tried to make your data talk.
I mean, technically, hypothesis testing wise, you would want it to be.
Right, yeah.
Right?
Yeah. It's close. It's 0.08. I think with more data points. Right, yeah. With way more data points, I think you would find something. Hopefully, fingers crossed. Okay. For Jamie's sake. Yeah. If you want to add more IVs, so I have model 3.1 here, because this is still fixed effects. So if I now want to add time, so I've got, I'm estimating my intercepts with a random intercept, and let's add the intervention plus also time. So are they just going down over time?
But this doesn't account for day?
No, not at the moment.
So what this is saying is like each day do they go down?
Yeah,
Like they start up high again.
yeah.
Okay.
That's why I said coding it as 1 through 25 or whatever would be a better way to do this. So all I've done is plus time out here. So add in time. Okay. Don't use a colon or a star, otherwise you're going to start doing interaction effects. So just do plus. So this variable plus this other variable. Okay, so I've run all of those, and I pasted that here. So time is not a significant variable. They are going down, but it's not significant. But because this kind of answers your question a minute ago, because I've included time now, you'll see that these p-values have also changed. So controlling for time, these are less fancy. Okay. So you can add multiple fixed effects, but I still would add them one at a time. And that way you can tell if something breaks, which variable is causing the problem. That's also a good way to figure out, okay, this didn't run. Let's back up a variable, see what happens. Often it's a multicollinearity problem. So the variable you've added second is too correlated with the one before it. Okay. Sometimes it's not, but generally that's the issue. That's when you go back and center them. And then the last thing is random slopes. Okay. Random slopes is if, like, within your IV variables, they should have different slopes. So going back to our Viagra picture, somewhere up here, I lost it. This would be random slopes and random intercepts. So people are just all over the place. I don't know if random slopes is always a good thing. I think it allows you to look for interactions if you find a significant random slope, but sometimes interpretation-wise, it would probably be better if it wasn't random. So that's kind of, I guess, a good thing, is that either outcome is interesting. So they're either not random and everybody has the same basic trend down, which is good for what your guys are trying to do, or they are random, oh, there's an interaction with this other variable going on, okay, that you hope you took the data on. Okay. So it's kind of like a moderation analysis. So that's when you might start to explore moderation instead of using a random slope, but this is how you would test for it. So we're going to change a different one this time. So we've been slowly manipulating where the ones are. And so we're going to add the variable we want to be random where the tilde 1 is. So here, where it says random, because that's where you change the random things, everything on this side is y, so it's changing the intercept of y. Now we want it to have a random slope, and we would put time here, because intervention didn't work. So I put time right here. So I could say, well, across time, they might have slightly different slopes, because if we're all starting in different places, maybe some of them are going down faster than others. And some of them are kind of flatlining, like they're like, oh, this is dumb, and they're just not doing anything. So that would allow me to account for the fact that people are going to vary their slopes.
Why does adding time there make that happen?
Make that variations in slopes. So instead of just a random intercept, so intercepts are always listed as a 1, right? It's saying, create me a random intercept, the tilde, and a random slope based on time. Because everything on this side is controlling for y. Like, everything on the left side is kind of controlling variable, like the intercept, and then the x variables. Everything on the other side is your nesting variables. So I'm not actually testing participant number, I'm controlling for that error. Yeah?
Why do you say intervention didn't work again?
It didn't run. I tried.
That's why we're keeping it fit.
Yeah. And you might be interested in, do the interventions have different slopes? Because they might, right? And so it might...
like picking out like what maybe is the most powerful of the 5 interventions.
Right, or maybe some people responded better to this intervention and some other people responded better to this one. So if they don't all have the same slope. Just most powerful wise, you can probably look at the coefficients, like which one has the biggest drop.
Okay.
But let's say this group of women, for some reason, this was a better intervention, but for these other women, this was a better intervention. What? It didn't run, but I don't think I have enough. I don't really have enough data at the moment to make it run. So that's why I said it's half made up, because it really should only be 4 time points in each intervention, but that definitely was like cranky. So, yeah.
I was just thinking, so to put this in a context of like, say like her study, when you're saying with the random slopes, it could be something like you've got, we're collecting data on, say, level of body dissatisfaction. So say you've got people who are high in body dissatisfaction, who you're going to give these interventions, their body checking is going to go down over time. But perhaps you've got people who are lower in body dissatisfaction and they don't have the kind of salience that you're used to. Now you're giving them these text messages that are telling them all about their body, and body checking actually increases their body checking behaviors. So that body dissatisfaction, level of body dissatisfaction is going to be that other variable that could cause that interaction.
Right. And if you didn't have it in the equation and you find random slopes, that's when you go, maybe we should add this as an interaction, and then the random slope should go away. Yeah, so I tried to create a picture by participant to show this would be an idea of random slopes, because some of them are going up and some of them are going down. But within the context of also including interventions. So I did the interventions all together, and you'll see the random slopes is not significant because these across time, we're getting all the same drop when you average them all together, but if you look at it by participant, not quite the same. And the bands around this is confidence interval bands. I love ggplot. I know they don't necessarily love ggplot, but I do. It's so great. Okay. So the other thing that I added here is just to show you, because this will happen to you at least once, where the number of iterations times out. So it's max iterations meet, no convergence met. And then it should have a little sad face next to it. So all that particular line of code does is allow you to iterate more. And so it's kind of, it got stuck and it didn't finish. And so that'll sometimes solve your problem where you need 11 iterations and it's only running 10. So that will turn up the number of iterations. Because if you leave that out, it actually does go, whatever, I'm done. So that tells it to do more math rather than less.
Would you do that if it ran? Like, would you see if it ran first?
You could. Yeah, I mean, the other ones clearly ran fine. Yeah. I think I didn't tell it to turn on all of the... You can tell it to also show you all the iterations, which is just way too much stuff for me. So I don't know if it needed, like it only ran 10 and it needed 12, or if it ran 10 and it needed 100, but I just told it to do the max.
Why'd you make it 200?
I think that's because that's what Stack Overflow told me to do.
I was just wondering if that's the magic number we
No,
use.
I Googled it and I found like this is what somebody did and it worked. I'm like, okay, cool. I don't know. I think it actually has a max that's like 150 or something. So it just the code ran.
So
Half
what if we made that like 1,000? Would that be...
It will stop when it's done.
Okay, so fail safe, make it a huge number. And
Sure.
you're good to go.
Yeah. You might be sitting for a while. Yeah.
I've done it with mice, so...
Yeah, that's true. That sounds funny if you don't know what mice is. Mice is a missing data imputation package.
I've done that with mine.
Yeah. Where we sat for a while and like let it run. Okay, so let's try this random slope. And so it runs because I forced it, like convinced it to talk. So with a random slope, I copy the fixed effects. So time, you'll notice the time variable between the two without a random slope actually switches sides. So it went from negative 0.02 from going down to going up. So 0.02. I mean, it's not significant, but it has like flipped because I've changed the random slope variable. So what does that mean? Good question. If I look up here, I can't make this thing go away, sorry. It gives me
Arrows.
Hmm?
Does not make it go away.
A little bit. not totally. It gives you the intercept value, right, and the time average, so across time, correlation here with the intercept, I think is what that reads. So across time, that's the standard deviation, sorry, I'm reading the wrong thing. So across time, it says now that I've let them be random, they are going up, but there is a fairly big range around that, right? And then there's an even bigger range around the intercept now. So remember, this is standard deviation, so it's how much they're varying. If we calculate each person's time slope and allow them to change a little bit, it's varying 0.2 around this 0.2. Okay, so some people are negative and some people are positive. And we talked about this in latent growth. If you do a random slope and the random slope is 0, that often implies that half the people are positive and half the people are negative. And the way to check for that is to make a graph by participant and see. Because right now the variable is not significant because some of them are positive and some of them are negative. So by allowing them to be random, it let them do that, but the average of it is still a wash. And that's where your interaction would help solve that problem. Maybe that's why it's doing this, is because of that other variable. Okay. All right, I know I'm trying to finish up here. And so I can compare all of those models and see if they're significantly different. Model 4 is not better than Model 3. So Model 3 is the one with time. Model 4 is with time and a random intercept, and they're not better than each other. Okay. Oh, wait, maybe it should be 3.1 there. Did I ever test if Model 3.1 was any good?
Yes.
No. Okay, so we should also have Model 3.1 in here. Because I compare, Model 3 is just intervention. Model 4 is intervention, time, and a random slope. So I've kind of left out one of my steps here. And they're really not different from each other. But you would hope they would be. Maybe not random slopes, because if you don't find random slopes, that's saying that the slope that you're getting is consistent across people. And that might be better for you. Yes, yes. The other thing that I threw in at the bottom, which I will not go over, is like all the craziness for ggplot, but I wanted to show you how I created the pictures that I did at the end. I have 4 or 5 videos on how to make these sorts of plots, and they're separated by type of plot. So this is a scatter plot with a line on it. So if you're interested in all of that, I can show you how to do that later, because I knew we were going to be out of time. And then the other issues that I didn't really cover is growth models. This is actually how latent growth models work as well, which you can run as a sim or as an MLM. There are different types of covariance structures that you can account for. That gets even more complicated in the stuff. So different types of correlated errors. And then there's not a good effect size. So most of the effect sizes, what people suggest doing is doing a ratio of log likelihoods. But the issue with that is that's actually how you would run the statistical test too. So it kind of seems like cheating to do it twice. So I was going to ask Kayla, figured out how to do some for her multi-level log regressions. And I'll see if I can make that work somehow for this. But there isn't a good version of effect size for MLM. That's kind of a trending topic because nobody's figured it out yet.